I know I don't have to use the mic, but it is being recorded, so I'm using the mic so that.
Yeah.
Hi, is this on? Is it on? And her mic is on. Morgane is on. Oh, great.
I think yeah, it is.
Oh, okay, great. Hi, everyone. So thanks so much for joining. I'm just going to get this going since I know that we want to have time for lunch. And we have members from the mezzanine as well. I just really very, very happy to have Morgane König here. And she is right down the street at MIT. But if you're wondering why you're surprised that I know anything about gravitational waves and inflation. I do not. But I met her through the MLK Scholars Program. She's an MLK postdoc at MIT. So I'll be certainly learning a lot today. And she did her PhD at UC Davis. And before that, she did her undergraduate at the University of Marie Curie in Paris. It's a much nicer name than the way I just said it, but maybe you can say it later. And we're also joined by our youngest PhD student, I think, ever, Aya, up in the mezzanine, and Max here to support Morgane. And yeah, really glad to have her here, and looking forward to learning more about things I have no idea about. Thanks.
Well, thank you so much for the lovely introduction, and thank you for the invitation. So it's going to be mainly a cosmology talk because I'm a cosmologist, but I hope that you find it interesting. So mainly when I started my postdoc, because I have a background in inflationary cosmology, it was the time of the discoveries of the detection, at least, of gravitational waves. And so I tried to kind of look a little bit into the future and ask myself, what if in 10 or 15 years, or maybe even sooner, who knows, we actually have a really good detection of the cosmological gravitational wave backgrounds. Cosmological meaning of cosmologic sources, not astrophysical sources. Then what can we learn from it? Is it something interesting? And so that has led me to basically lead a project with two really wonderful graduate students, one at Pittsburgh, Marcel, and one at Brown, Tats. And I'm also this is important for me because this is also some of the few papers only by Black physicists, and I think we do also really good work together. And so those two papers came out, they're on the archive, and they've both been accepted by JCAP. Okay, so the story starts by, as everybody knows, the detection of gravitational waves by LIGO, which was very beautiful and opened a very new avenue in astrophysics and cosmology. Now we're not only able to look at the universe through photons, we can also hear them through gravitational waves. So now I don't think I have to explain how this works. It's an interferometer, gravitational wave goes through it. The branches are going to lengthen or shorten, is going to induce a phase distortion, and we're going to be able to say that we detected a gravitational wave. So this is the frequency spectrum of what we can look at. In the higher frequency, we usually look at black hole binary mergers. On the very high frequency, we detect something we actually do not know the sources, so that's also an interesting avenue to look at. But what I'm interested in is more the low frequency of the gravitational waves, because there we can look at the stochastic background. Last summer, I think it was in June, Nanograv actually came out with a detection, the first detection of the gravitational stochastic background, but that was, which is very interesting, but that's mainly of astrophysical nature. So that's mainly made out of black hole binary mergers. But we're hoping that we can also get some from cosmological nature, mainly coming from either phase transition, inflation, bubble, any kind of phase transition mechanism earlier. So now the technology is a little bit different. When we look at the higher frequency, it's mainly interferometer. When we look at low frequency, it's mainly PTAs, pulsar timing arrays. So how does that work? The way it works is we can look at pulsars, which are rotating neutron stars. And again, I'm sure that the audience knows more about it than me. But basically, we can think of pulsars as the astrophysical equivalent of atomic clock. And when the gravitational waves go through those pulsars, it's going to induce a shift in the pulses and then indicates that we have a gravitational wave. So it's a little bit of a different technologies. I mean, this is kind of the idea. We have all the pulsars here giving information to the Earth, and then when a gravitational wave goes through it, we have a little bit of a shift in the pulse that it gives. Okay, so then I know that this is a long shot to try to think about getting a stochastic gravitational wave background of cosmological nature, but it's still important to think about it. The reason why I thought it was important is because when we think about the CMB, we realized that we were able to get a wealth of information. I mean, now Planck is basically giving us almost everything we know about cosmology. It's, for example, confirming the fact that we have dark matter. It's giving us basically all the amount of elements in the universe. But it did take 50 years to be able to get a map that would give us all of this information. From, again, 65 when it was theorized to the first detection, COBE, which was great, but again, couldn't give us so much information, to finally getting a beautiful map of Planck. So even though it's a long way, I consider myself a young scientist, and I think it's still an avenue that is worth investigating. Okay, so the stochastic gravitational wave background, again, as I mentioned earlier, first of all, what kind of sources are we looking at? We're looking mainly at gravitational wave produced by inflation, gravitational wave produced by phase transition, by very early universe mechanism. And we're just going to take the following assumption. We're going to assume that it's stationary, we're going to assume that there's non-Gaussianity, we're going to assume isotropy and polarization. Just basically the simplest assumption at first to try to get some information about a potential stochastic gravitational wave background. Now, what we're measuring is not the change in temperature, but it's the spectral density for the fractional density. It's basically the ratio between the amount of gravitational waves to the critical density. And so, I mean, I don't know if this is so interesting, but this is, maybe I'm going to skip that. This is basically just the nitty-gritty of gravitational waves. How do we detect gravitational waves? We start with a metric, we perturb the metric, we get the equation of motions, and then we're able to access a primordial spectrum. Okay, but no, what's interesting here is, again, what is going to be measured by the cosmic gravitational wave background, this omega parameter, which is again connected to the amount of gravitational waves, is also connected to here, this n parameter here. And n is the number density of gravitons. And so we can really look at the stochastic gravitational wave background as giving us information about the change of gravitons with respect to their frequency. And the reason why this is interesting is that, again, you're astrophysicists, so you probably know that even more than me. That should ring a bell. That actually sounds a little bit like, so I'm going to skip. Well, maybe I'm just going to advertise it first. This sounds a little bit like something called the Sunyaev-Zardovich effect, where there was also a difference in the occupation number of the photons. Okay, so again, just to emphasize the fact that there's two different ways or two different kind of stochastic background. There's the one of astrophysical nature, which is made out of black hole binary mergers, white dwarfs mergers, and there's the one coming from cosmological sources, again, inflation, phase transition, etc., etc. On my work, I really kind of focus on the source on inflation being one of the source of the stochastic gravitational wave background, but again, there's a lot of different sources. Now again, I think we have pretty high evidence that we can get the astrophysical background. It's a little bit more tricky to get the cosmological background, but I hope that one day we will get there. So again, the question is, if one day we get the gravitational equivalent of the CMB, what kind of information and what kind of cosmology can we do with it? Okay, so again, I mentioned looking at the occupation number of graviton. And that, I think, was very interesting because it reminded me of this SE effect, the Sunyaev-Zeldovich effect, which is the following story. So what we have is we have photons emitted by the CMB. Those photons are going to traverse an enormous amount of the universe. They're going to interact with electron in the intragalactic medium through Compton scattering. Because of that Compton scattering, those photons are going to gain energy, and this is going to induce a shift in the intensity spectrum of the CMB. And this gave enormous amount of information about the intragalactic medium in the galaxies. So now the idea was, can we think about doing something similar, but instead of looking at the change of occupation number of photons, we could look at the change of occupation number of gravitons. And instead of looking at photons interacting with electrons, maybe we could look at gravitons interacting with something else. But first, we had to understand the assumption and how the SE effect came to be. So the SE effect really was a solution of the Kompanitz equation. The Kompanitz equation, the establishment of thermal equilibrium between quanta and electron, was established by this wonderful astrophysicist. And again, here I always tell this anecdote because this was done in '56, and this was financed by the Russian equivalent of the H-bomb program. So Kompanitz took the money and said, yes, of course, I'm going to help you figure out the H-bomb, but did something completely different. When they figured it out, it was declassified. Now, if you notice, it's also translated in English because the CIA was also looking at everything that was coming out of Russia.
Kompanitz was in his group, and Zeldovich could not speak because of classification.
See, I did not know that.
Yeah, Rashid Sunyaev told me the entire story.
Wow, okay, this is super interesting. I had no idea. Okay, well, I'm learning something every day. But again, I think this is really cool because it's really part of like the Cold War history, basically. And so what Kompanitz or Zeldovich did, apparently, is basically look at a thermal bath of photons interacting with a thermal bath of electrons and look at how this would change the occupation number of photons. And so here there's really two mechanisms that comes into play. The first one is a stimulated emission, meaning that we can have photons going from one energy level to the other one. And the second one is a Compton scattering, which basically tells you that you're going to have some change of the occupation number of photons due to the Compton scattering, due to the interactions between photons and electrons. So again, here is just to explain it a little bit. So this is just looking at the stimulated emission part. So it's actually quite simple. The first line is just the flux. Okay, this is what happens when we go from a final state to an initial state. Then we have the creation and annihilation operator. And now we can look at the change of occupation number of the photons at a particular frequency. Here there's going to be two parts. There's going to be the photons that disappear, so the one that go from K to K prime, and then the one that appears or are created that go from K prime to K, hence the minus sign between the two. Now we can also assume that there is symmetry and that the total number is conserved, and so we can get the final master equation. This is only taking into account the stimulated emission, but then we can also take into account the Compton scattering, which is going to come here into play in the fact that, again, the stimulated emission only changes the occupation number of photons. The Compton scattering is going to change here the occupation number of photons and electrons. The non-covariant transition rate has all the information about the interaction between electrons and photons. Here we can assume that the electron bath relaxes faster than the photon bath, which simplifies everything. We can also assume a Maxwell-Boltzmann distribution in momentum for the electrons. And finally, what we're going to do, because this would be too difficult to solve, we're basically just going to do a Taylor expansion in the change of energy to simplify everything. And this leads to this beautiful Kompanitz or Zeldovich equation, master equation here, where this is just a second order, but it's already great, where the information about the interaction is hidden here in those I1 and I2. So here I1 and I2 basically tells you the level of the leading order that you're looking at. Okay, so now what they did is they solved it, which was easier in the case here of the Compton scattering between photons and electrons, and they were able to get this beautiful equation that is known as the effect that tells you basically the change of occupation number of the photons, and that is translated into a shift in intensity. So again, this has been basically just something that has been known for a long time that I had to teach myself again, but I think this is very beautiful. So now how is it related to the research that I'm doing? Again, what if one day we're able to get a stochastic gravitational wave background? What if one day we're able to access the difference of occupation number of graviton? What can we do, and what are the biggest problems that we have today in cosmology? So one of the things that people are doing a lot at MIT, and I think in a lot of places, is looking for those goddamn dark matter. What is it? And I think the community is doing an incredible amount of work, but unfortunately we're not looking at it, we're not finding anything. So here is just a little bit of a reminder of how we're looking for dark matter. We can look at indirect detection, assuming that basically heavy dark matter is going to annihilate and give us gamma rays. We're looking at gamma rays excess in the galaxies. We're trying to figure out the one that do not have a source and say, oh, those probably come from dark matter annihilation. We can try to produce them in collider at CERN, for example, and try to understand their properties. And we can also build, or actually we do build, a very impressive xenon tank, hoping that the interaction between a WIMP, pretty heavy dark matter, and a xenon nuclei would produce a scintillation, which would tell us that we actually have observed a dark matter particle. But in my opinion, I mean, those are really beautiful, and I think this is great, but the problem is we're not finding much. First of all, the xenon, if we don't find anything with that method, I think the funding is going to be done in a couple of years. I think that the gamma ray was amazing, but this has been going on for 10 years, maybe even more, maybe 15 years, I don't know. And this is also not doing anything. I think there's a strong assumption that is a logical assumption, but there's an assumption that we think dark matter should somehow interact with the standard model. I mean, weakly, but we still think it should interact with the standard model. Now, the weakest assumption that we can make about dark matter is that it interacts with gravity, because it has a mass. And so what if everything else fails and we're left with saying, okay, dark matter only interacts gravitationally. How can we use gravitational wave detection to try to understand dark matter? So here what I wanted to do is basically look at a gravitational SZ effect. So instead of looking at the cosmic microwave background, we could look at the cosmic gravitational wave background. Instead of looking at photon-electron interactions, we could look at graviton interacting with beyond the standard model, maybe not to say dark matter for now, through Compton scattering. And then we will have to solve the gravitational compensation equation and see if we see a similar shift in the intensity spectrum of the graviton and see if this is something that would be potentially measurable one day. Yeah?
So classical physics is the limit of quantum mechanics at large occupation number. So when we talk about gravitational waves classically, it means that the occupation number is huge.
Right.
Tremendous, much more than photons usually.
Right.
Right? And so is that true for all the cosmological backgrounds, that the occupation number is like huge?
What we've looked at is it was actually quite small.
Oh, it's not.
And what we're really worried about is actually not the absolute value of the occupation number, but the shift of it. This is what we focused on.
Okay, so it is significant.
And, yeah, and so, right. Now, but that's a good point, and maybe something I have to think about. Another thing that I have to think about that so far no one has said anything is I have said the word graviton a few times, yes. And my colleagues at MIT, oh, well, we haven't found graviton, what are you talking about? If we look at low energies, basically gravity is a theory described by a massless two-spin. So we can describe it as
there is a debate that started with Freeman Dyson as to whether we can detect the graviton.
Exactly. And I'm not claiming that we can detect the graviton. I'm just using it as a tool.
Right.
But again, because we're always at low energy. Yeah. Oops, no, the other way. Okay, so I'm going to give the spoiler here. So we looked at basically dark matter as spin 0, spin half, spin 1 particles at different masses, and we try to look at this difference of occupation number. And we found a very, very small number. I mean, mainly this is not going to be detectable. But we thought it was interesting because I really wanted to basically put, look at the formalism and start looking at this graviton interactions. And then it led us to something actually quite interesting. We actually thought, what if we look at primordial black holes as dark matter candidates in the mass range when it makes all of the dark matter? And then actually we have a much larger effect. And so that's starting to get some interesting. I always say that maybe the, the good thing about being a young, naive scientist is we kind of get headfirst in project that maybe senior scientists would say, no, it's not going to give you anything. But then maybe we get a bit lucky and we find interesting things. Okay, so here there was some assumption that we had to make, or that we had to make sure also apply in the gravitational case. The first one is that the electrons are in thermal equilibrium. Here we know that beyond the Standard Model, or at least the dark matter particle that we're looking at, are in thermal equilibrium. We're also only looking at cold dark matter, which means that the particle that we're looking at are non-relativistics, and the graviton that we're looking at are also soft. So here we could actually basically one by one take the companions equation and then we had to solve it. Now, of course, there's a lot of differences and there's a lot of subtleties. The first one is that we are not looking at photon-electron Compton scattering. Now we're looking at graviton interacting with spin half, spin 0, spin 1 particles. And so this is also a bit more complicated, and this is going to come here in this term. The second difference is that we could not ignore the terms here because in the case of photons, electron, the temperature of electrons is way higher than the temperature of photons. So that simplifies the equations quite a bit. Here it's not the case. So the equations turn out to be a little bit more complicated. And I'm going to go maybe a bit more into it. So first of all, we had to try to figure out a way to get the differential cross-section looking at the interaction between graviton and our dark matter candidates. So here it looks fine, except that there's a little bit of an issue here. So because of this graviton interaction, this actually induces some IR divergences. So here, sorry, if I go back here, in the companions here, we could just look at 0. There was no problem, there was no divergence. Here we had to basically put a cutoff, otherwise everything was going to blow up. So we had to find a way to, in a smart way or a way that's consistent, at least put a cutoff for the IR divergence. It's a little bit the same thing as the Coulomb IR divergence, similar idea. So to do that, we basically invoked the geometric optics limit. This is the idea that, so this here is the object that this is our dark matter candidate, for example. So it could be a particle, it could be a black hole, and then we're going to have the graviton coming from this side interacting with this. So now we can define a region where we don't have to worry about quantum effects, and we also don't have to worry about optics effects, meaning, for example, diffraction, or all type of optics effects. And so we took the subscription from those lovely people here. What they do is they basically define a region based on the fact that this can be described as a Schwarzschild metric, and we're able to find an upper bound on the impact parameter that would avoid us the complication of having to take into account geometric optics or optical effect, like diffraction, as I mentioned earlier. And this upper bound on the impact parameter actually gives us a lower bound on the angle of interaction. Yeah.
So is this like still the case of like particles, or was this like a primordial black hole?
You can do that with particles. Yeah. So with particles, the metric that you would take would be a little bit different, but effectively it would give you like almost the same cutoff. Yeah.
I'm a little bit confused about the forward scattering because usually forward scattering gives you an index of refraction.
Yeah.
In optics, you get some forward scattering amplitude and
Right.
you put it into the index of refraction. So it basically changes the phase velocity of the wave. That's all. So if you have scatterers,
Right.
you can add them up and it changes each of them gives you a spherical wave.
Yeah.
And you sum them up and you end up with another plane wave, and altogether it's a change in phase velocity. And that's the standard description of
Yeah.
an index of refraction. So are you
So
excluding that here? Or?
here, what we really focused on really was one-to-one interactions. We didn't look into all of the subtleties.
This is more of the
It's one graviton interacting, but that's a good point.
Sorry?
It's very dilute scattering medium.
Yeah.
Yeah, so this is a higher order reflection. It's just looking one-on-one interactions, not the collective effect.
So for that to be the case, the separation of particles is bigger than the wavelength?
That's right.
But is that true for primordial black holes?
No.
No.
But that's a good point, and we're gonna get there. For now, we just looked at one-to-one interactions,
Okay.
but then actually this is something that we can also look more. And the other thing is we assume one graviton would interact with one PBH, but maybe actually they interact with a collection of them, right? And that would actually give us, and this is something that we also looked into. For now, we just looked at the simplest case. Yeah, but yeah, that's a good point. So anyway, so this was, as I was saying, this gave us a lower bound for our angle, which was able to basically help us with this cutoff problem that we had with this IR divergence. So here again, just to summarize it, we have the Kompanitz equations, we have those JL that, again, contain the information about the order that we want to go into. Here we also assume that we had a Maxwell-Boltzmann distribution in momentum for the dark matter. Here we have the information about the interactions between graviton and our particles. We're able to figure out a higher bound for the impact parameter using the geometric optics approximation, which gave us a lower bound for the cutoff angle, which basically help us get rid of the IR divergences. Now again, this gives us a first estimate. I'm not saying that there's not a better way to deal with the IR divergence, and I would be happy to hear anything or any suggestions. Okay, so without going too much into the detail, but actually that took us an enormous amount of work because we had to basically find a way to access the differential cross-section for those interactions. So this is the interaction that we're looking at. I'm just taking the scalar case. This, first we try to do it with the good old Feynman methods, which was horrible. So then we actually had to learn a bit more about the spinor helicity business, which at first was also horrible, but at least it gave us a result. So we were able to at least access something somewhat sound, and this is basically the scattering amplitude that we get for graviton interacting with the spin 0 particle. And then for spin half and spin 1, it's the same thing, we just add some terms. All right. Another thing that I have to mention is, but I already mentioned that I think, so now we also need to consider a source for the gravitational waves that we're looking at. And so what we looked at is gravitational waves produced by inflation, but in particular gravitational waves produced by single field inflation because it was just the simplest case. Now I know that single field inflation is not the most likely scenario. The most likely scenario is multi-field inflation. It's actually also what I worked on my PhD. But it was just to get a first approximation, and then we can also refine this. So, but when we look at single field inflation, we have a pretty simple equation that gives us the occupation number of our graviton, and so at least we're able to again get it started and get a first estimation. Okay, and this is the result. It looks not very nice, so let's just look at the plots. So we also had to look at the optical depth a little bit for a sanity check, because we wanted to make sure that most of the interaction between our graviton and our dark matter particle would actually happen very early in the universe, which is the case. 10 to the 5. And so what we realize is that there is indeed a shift in the intensity spectrum here that is also spin dependent, which is again not surprising because the differential cross section is heavily spin dependent. So again, this is a pretty good result in the sense that we were able to actually conduct the calculation to fruition. Now again, I'm going to be clear, this is not going to be detectable. Here we have, we rescaled it, but this is not going to be detectable. So I think it was interesting to again lay out the formalism and try to see where we can go from there. The problem, of course, is that when we have something that is Planck suppressed, we either have to find a way to enhance it or we have to find mechanisms so that the signal would be way higher. But it was still, I think, a good exercise to do it. Now, while doing it, we also thought, what about primordial black holes? I mean, primordial black holes are also still a viable candidates for at least some of the dark matter, if not all of the dark matter, especially in this region here, in the asteroid mass range. Here they can still make up all of the dark matter. So this is interesting because we can either, realize that primordial black holes make all the dark matter there, or we can maybe find a way to put constraint on this unconstrained parameter space. So this is what we did, and now again, PBHs are a very different kind of object. First of all, how do we really define the temperature for PBHs? And so for this, we looked at the Hawking temperature. And again, I'd be happy to discuss, maybe there's better ways to do it. So we just thought we're going to look at the Hawking temperature instead of just looking at basically the thermal temperature. Those are non-thermal, so that was the main difference. The second thing that we did is we said, okay, we're going to assume a monochromatic mass distribution, which I also know there's a lot of discussion about it. This is just an approximation. There's a whole discussion about there's a Gaussian with a tail. And so this is a simplification, but at least for first approximation, it seems to be working. And we're also going to, as I mentioned earlier, we're going to look at primordial black hole of asteroid mass range, so 10 to the minus 16 solar masses. And when we did the similar work with PBHs this time, we actually got a result that was pretty interesting. So here we saw a distortion of basically 0.3% if we look at, again, the change in intensity of our stochastic gravitational wave background produced by single field inflation. So there's a lot of assumption, but here we actually saw something quite interesting.
This is the mass units of the black mass?
Yeah. No, of the mass of the black hole, yes.
Yeah, but the units of the black mass. So in other words, the units of mass is energy, but you have mass to the -1, so it must be the Planck mass squared over mass or something. It's omega divided by the Planck mass squared over mass, right? That's what it is. There should be a Planck mass squared in the denominator.
Okay, yeah, I have to think
just
about
to get the units correct.
Right.
Yeah.
Okay.
So I guess when you say 1, that corresponds really to not the mass of the black hole, but something else. The frequency that you get most of the effect.
Yes. Yeah. So another thing maybe that I failed to mention is that here there's an enhancement, meaning that the gravitons are going to gain energy, and here it's actually negative, which means that basically the gravitons are going to lose energy. So it's actually, it looks like this, right? So it's just another, which makes sense because if some of them gain energy, some of them have to lose energy. And then again, another thing is that some of our colleagues pointed out, but I mean, you have a graviton interacting with one primordial black holes, but what if actually you have some length scale that tells you that the graviton interacts with multiple primordial black holes? What would that give you? And actually that gives us, so this is exactly what you mentioned earlier, that gives us an enhancement, right? In the fact that we also have to look into the distance between the PBHs versus the lengths, the wavelengths of the incoming graviton. And so here we actually also looked at a case where we assumed that the average spacing was 10 to the minus 3 parsecs. And what was interesting in this case is that it actually gave us an enhancement of 70 to the power 2/3. So basically here we went from a 0.3% shift in the intensity to a 5% shift. So I agree with you that that was actually very important. Again, in the beginning, we just wanted to, to do the simplest thing, to look at one-to-one scattering, but of course, in reality, that it's probably not what's happening, and we have to look into those mechanisms. And actually, it gives us something very interesting. So yeah, 5% shift is non-negligible. It's also not enormous, but it is non-negligible, especially coming from looking at graviton interacting with dark matter, which gives us basically almost no detectable information. So so this is interesting. So again, what I really want to emphasize with this talk is that I think that there is a lot of new physics that we can do, especially on the cosmological side of things, with gravitational waves. I know that in astrophysics, it's been something that I think has been done a lot. In cosmology, I felt like it took a little bit of time for the community to actually look at gravitational wave detectors and see it as something very interesting. Something that not only is going to give us information about black holes and how black holes function, but can give us a lot more information about, again, dark matter or potentially dark energy. So I think there's a lot of physics that can be done there. So again, here is just maybe a to-do list. We have to look at different sources of cosmological gravitational wave background. Mainly, I think, other scenarios for inflations. We have to try to figure out maybe a better way to think about the cutoff issue. And then we can also look at different kind of dark matter. We can look at dark matter composites, something that's maybe a little bit bigger, something that has a higher spin. I don't know. And then we can expand the formalism to other interaction processes. So one thing that we were thinking about is trying to see if we can use it to understand the sources, potentially the sources of high-frequency gravitational waves. And I'm not going to talk about it too much, but anyway, this idea of really looking at graviton interactions could be done in maybe other scenarios. So thank you.
I know we already had some questions, but we have time for a couple more questions. Yes, I'm going to go this way, if that's all right.
Yeah, thank you. I have a question on is there any intuition as to why the spectral distortions from the primordial black holes would be much greater than the ones from just the dark matter particle model?
Yeah, so you can think about it in the way that, first of all, they're way more massive. They're huge, right? The dark matter candidate that we were looking at were very, very tiny. And then there's also, and maybe I went a little bit too fast on it, but there's also a way to define this cutoff business. So when we look at a dark matter particle, what actually makes sense is the Compton wavelength. But when we look at a primordial black hole, what makes sense is the Schwarzschild radius. And so that also is going to play a role in why we have a bigger effect for PPHs.
Yeah, thank you.
Thanks for the talk, it was really nice. I had a quick question, just also maybe a naive question, that can you also detect something like a KSZ effect, like a kinematic scenario-visual effect?
So yeah, we thought about it. We thought about looking into it, and I cannot give you an answer. We have to do the work. But this is definitely something that we have to look into it. But now I think maybe you can tell me more about it, but then I think we may have to relax the non-relativistic assumption, which makes everything way more complicated.
But then the idea would be that if you have a large scale, a bulk flow of this dark matter, then would graviton interactions also get affected by just this fluid velocity of a dark matter?
Yeah, they would. But again, remember that when we look at dark matter as particles, basically we're not going to get anything. So we also have to be conservative on how much effort we're putting there. But yeah, that's something that we also thought about. Yeah.
Thanks.
I have a naive question. If you could go back to the last slide you just showed. With the cloud of particles, yeah. Why should we be thinking that this would be the right sort of geometric picture?
That's a good, sorry.
It's a great thing to explore, but I would think that this would be something that would clump into, into a very different distribution.
Yeah, yeah, absolutely.
So
That's-
is that considered, or
Yeah,
can it be
this is
considered?
exactly something we're thinking about. This is a very good question. Yeah. I mean, so first again, we naively looked at the enhancement, but we also have a limit on how close they can be together.
Mhm.
Yeah.
Thank you, Josh. Yeah, so recalling what I know of the SZ effect, right? We start with the CMB, which has some temperature. So it makes a black body spectrum. And then the SZ feature is, like you said, a shift from low energy photons become higher energy through scattering. And the feature is actually present near the peak of the black body spectrum, which is 100, 200 gigahertz or where. That's where the sign change happens. So the whole effect is determined by the spectrum of this background radiation, the photon radiation. I'm unclear. What is the equivalent quantity here for your gravitational wave background? Is it also a background with a temperature of 3 degrees Kelvin, and so the effect is seen at a few hundred gigahertz? Or, what is it? What is the equivalent? At what frequency should we be looking for this
So
effect?
it's going to be at all frequency, actually. So that's maybe one of the difference with the SZ effect. So this is going to be a shift that we're going to be able to see through all frequencies. Now I'm not sure. So the CMB has a black body. Now the equivalent would be basically the distribution of graviton that we have, depending on the source of gravitational wave that we're looking at. So it was what I was mentioning, I think, earlier with this, basically. I think this would be maybe the equivalent. So instead of having a black body radiation, this is the assumption that we're going to take for a graviton, if that makes sense. Because the black body radiation really comes from just looking at stimulated emission, right? And then we just solve it, and then we have it. Here this would be the equivalent. Now again, the effect. This is also something. The effect is going to be through all of the frequency spectrum. It's not going to be at a particular point. I know this is a question that came a lot, and maybe I have to articulate it a bit better. But it's not really just picked at one.
This is like the Rayleigh-Jeans slope, isn't it?
Sorry.
This is X is the frequency, right?
Yeah.
So in the Rayleigh-Jeans part of black body, alpha is -2, isn't it?
Yeah, that's true.
Yeah. So
Yeah,
it's like the
that's true.
Rayleigh-Jeans regime. I mean, this
Yeah.
particular model.
Yeah.
So you can get a shift in the Rayleigh-Jeans.
So also the temperature, or maybe if there's a corresponding. Oh.
Yeah, I don't know what the temperature equivalent would. I mean, again, it's this omega.
It's not thermal. It's not a thermal process.
It's exactly.
It's inflation is scale invariant most of the time, so there is no scale. A temperature requires a scale, where in inflation it just gets scale invariant.
That's
But
right.
you do get a slope, which you
Right.
pointed out, it resembles the Rayleigh-Jeans.
That's true.
Yeah, also, the nature of stochastic gravitational background highly depends on the sources, right?
Yeah.
We actually don't know. The short answer is we don't know.
No, that's true.
Yeah. So
Yeah.
you hypothesize some kind of mechanism. You have completely different gravitational wave background.
That's true.
Yeah.
Another thing to keep in mind, if you have not inflation, but if you have a process that is causal, let's say a phase transition, then obviously there should be a cutoff at the wavelength corresponding to the horizon by causality. So this power law is only because inflation continues for 60 e-folds. So it's a huge stretch of scales. But during a phase transition, you have a cutoff at the horizon scale. So it would be it would be like a spectrum that has some slope and then cuts off at some long wavelength.
Yeah, that's what people typically.
That's true.
Great, some great questions.
I just want to take the last 10 minutes to talk about something a bit different. It's not physics related, but it's kind of physics related. So as an MLK scholar, I think it was also important for me to maybe look at the contributions of different people into the field of physics. So here I just took a picture of the CMS, and there's a lot of people. But what I noticed is that there is almost no participation from the African people, right? So here in the US, we already have a little bit of a problem when it comes to representation of different people. It's mainly a certain group of people that is predominant. But overall in the world, it is also a problem. If we look at the people working at CERN, it's very much dominated by Europe, America, and Australia, actually. And then yeah.
What are the colors? Can you explain?
So the colors are member states, so they're described here. Member states are in blue, observers, and then others.
Ah, okay.
Yeah. So it's mainly a European.
So your point is that, especially in Africa, it's mostly white.
Not only is that mostly white, but we can also look at the actual number of people in each country. So if we look at, for example, Swaziland, we have 1. Sudan, there's 1 person. Zimbabwe, 2. Zambia, 1. So I think overall there's maybe 30 people out of thousands of people. So there's really like a lack of participation of African scientists or African people in most of the most important science in the world. What we also looked at is the output of journals recognized by Nature. Most of them come from Europe. Then second we have Asia, North America, and then of course also other continents. And this is important, and we can say, oh, Asia also has a lot of participation, but it's important to also take into account the amount of people there, right? And so, exactly. If we actually look at, if we take the ratio, then this is more important. So this is the research output per 1 million population. North America dominates, Europe and Oceania, mainly Australia, dominates. Asia is present, but at a much lower participation. And Africa here is abysmal with 0.22. And so I think that this is something that is important to talk about as a community, because the future is in Africa. I mean, in 2050, I think most of people under 35 will be on the African continents. Now, we will be facing an enormous amount of challenges, climate change, etc., etc. And so it's important to try to give, not only to say we want to give African people the tools, to help each other, but I think we have to think in terms of humanity. I think it's important to give the next generation of humanity the tools to solve the incredible challenges that are ahead of them. So this is, again, a projection of the population. We can see that the African population is the fastest growing. And here again, it's just, again, another graph to see that the African population is just increasing dramatically. And so it has come to my attention that I have given talks mainly in Europe and in the US. I would love to give talks in Asia. Now with a baby, it's a bit more complicated, but I would love to go, and I think maybe it's possible, but I would not even know where to go in Africa to give a talk. I think that, again, there is no real physics community there. And so that has led me to try to brainstorm with some of the colleagues in MIT, especially Thomas Steingasser, who is also Dr. Thomas Steingasser, who is also a postdoc. And we kind of came up with the idea of trying to set up what we call some sort of an Africa symposium. So the idea is to go to different institutions in sub-Saharan African countries for 3 days and to try to expose them to the research that we do, and also to try to understand the research that they do. So we really want to do it as a collaborative way, and we want to brainstorm and make it happen really on both sides. We don't want to come and say, hey, we want to give you the amazing science that we do. I think we do amazing science, but I think it really has to be built on both ways instead of just going and being patronizing. So to do that, we actually reached out already to 4 different professors in several countries. So I think we talked to someone in Cameroon, we talked to someone in Ghana, we talked to someone in Côte d'Ivoire, and we're also in correspondence with someone from Congo. And so this is something that we would really want to see happen maybe in 2025 as a way to bring or at least to try to start bridging the gap that we have between the global north and the global south. I think it is incredibly important to motivate and to inspire the younger generation to get more involved and more interested in physics. So far we have had some support from some entities at MIT. We also have some support from some universities in Europe, and we're hoping to hopefully maybe get some support from the Harvard crowd, if this is something of interest. I really want to emphasize that something like this has never been done. There has never been universities from the global north going to actually host or collaborate or want to meet the scientists and the local population in sub-Saharan Africa. So this really would be a first. And I think this is something very important as well. All right, thank you.
All right, thanks. I think we need to break unless anyone has any questions to set up for lunch. And then I guess Morgane will tell us something else on her research set.
Yeah, we'll meet in half an hour.
All right, thank you so much for coming.
Yeah. Thank you for giving me the platform.
I know. I mean, I was like passing this with you. I know that I had to teach it. And actually, I took some pictures over here with you.
Oh, great.
Your
Yeah.
Yeah. Well, in your material.